In the past few videos, we covered a lot of groundwork, so in this one, we're going to use some examples to consolidate everything we've learned so far. I'll also show you some tricks that will help you debug and understand your programs better. Say we want to make a function that sums up numbers from 1 to n. First things first, we need the type. It takes an integer n and returns an integer that is the sum from 1 to n. So we have int arrow int. So from the arrow, we know we need a term with an arrow. So we can say n of type int with a result of type int, arrow, n times n plus 1 divided by 2. We can also give this function a name using a let binding and put the type annotation on the name instead. So we say let direct sum from 1 to of type int arrow int is equal to n arrow n times n plus 1 divided by 2. But we don't actually need any annotations. Why is that? Because when the compiler looks at that expression, it uses recursion to break the expression down, find the types of the easy cases, then build the whole expression's type back up from the smaller parts. Since it's a function, we know there's an arrow in the type, but we don't yet know what the two sides of the arrow are, so we call them A and B. Then we look at each part of the arrow. We can't get very far with the left, so we go into the right and hopefully that works out. We know star has type int comma int goes to int, so that means n needs to have type int, and so too does n plus 1 divided by 2. We then continue this process upwards for divide and then plus to make sure there aren't any conflicting answers. For example, if we had accidentally written double plus instead of plus, the compiler would be confused because for star we need n to have type int, but for double plus we'd need n to have type string. You don't have to do this every time, but it's good practice to do it every now and again when you're confused. Now let's get some practice writing recursive functions. After you see this example, pause the video and try writing a recursive version of the direct sum function above, applying what you learned. Let's take a look at choose. We know it takes two numbers and returns a third, so its type should be int comma int goes to int. We can write let choose from equals k comma n goes to choose from k minus 1 comma n minus 1 plus choose from k n minus 1. If you try and run this, you'll probably get the error unbound value choose from. This is because Reason requires you to be explicit when you use recursion. You'll see why making a distinction can be useful in a few moments. So let's fix that. Instead of let choose from, we write let rec choose from. Now, this isn't going to work. Get ready to hit Ctrl C and then try running it, say with choose from to 3. You'll probably get a stack overflow during evaluation brackets looping recursion error. So there are a few ways of figuring out what's going on. You can either stare at the code, which for simple things might work, but it's usually a bad idea. If you missed the error while writing, you might miss it while reading. Try a few examples. Does it give you the same error on all examples? If not, try and find a few examples where it works and a few examples where it doesn't. Or you can use pen and paper. This is my preferred method, and it's a good way to get started with functional programming. It's a really useful and powerful skill in the long run, and you'll quickly be able to do it in your head. So first thing you do is write down choose to 3. Then from the definition, we know that this expands to choose from 1, 2 plus choose from 2, 2. At this stage, left or right doesn't really matter, but let's go with right because that's what Reason likes to do. We expand the right to get choose from 1, 1 plus choose from 2, 1. Again, we expand choose from 2, 1 and keep going. We have choose from 1, 0 plus choose from 2, 0. And we keep going to get choose from 1, negative 1 plus choose from 2, negative 1. At this stage, we kind of scratch our head and realize something's gone wrong. Choose 1, 0 and choose 2, 0 should both be 0, but this keeps going past that. We've forgotten our base cases, so we fix the code. we have an if statement saying if k double equals 0, double bar for or k equals n, then we have 1, else we have what we had before. More concisely, we can write it with a question mark, k double equals 0, double bar k double equals n, question mark, 1, colon, choose from k minus 1, n minus 1, plus choose from k, n minus 1. Now we run it and we see that it works. So the lesson here is to always remember your base case. Remember, induction is the same as recursion, and that's the same as having a base case and an inductive step. On the screen is some code to help you generate Pascal's triangle. You don't have to understand it for now, but I suggest you type it in and see what it does. Expression expansion and evaluation is a key skill, and you should always try it first. But sometimes you do it wrong, or you're just feeling a little bit overwhelmed by the recursion. So you can use the oldest trick in the debugging book, printing. Even languages like Haskell and Idris support this, but as we go on, we'll see how to structure our code such that printing becomes the last resort rather than the first. So the first thing you can do is modify your original choose from functions, and you can say let rec choose debug equals k comma n goes to open curly brace printf.printf with this format string kn to print a line with the values of k and n, and then call the function as before, choose debug k minus 1 n minus 1 plus choose debug of k and n minus 1. Now get ready to Control C and run it. You'll see that it prints out a lot of output, and you'll see choose debug is running into negative numbers, which is not what you wanted. But the risk with printing is that you might print the wrong thing. Why won't the code on screen work? Pause the video and use expression expansion to justify your answer. The problem with print statements is that they make the code uglier. You have to put them in. Although it's really easy to print a primitive type like int or a string, what about something like a list or a record? Then you're writing a lot of code every time you need to debug something. So here's a trick that will be useful later on. Don't worry if you don't understand it right now. We'll get familiar with higher order functions in the next video. The first thing you do is remove the rec from your function and change the name to something like choose no rec. The second thing you do is add an extra argument called recurse on. Then you replace every place in the body where you were recursing using choose from with recurse on. So this looks like let choose no rec equal recurse on, comma k, comma n goes to recurse on k minus 1, n minus 1 plus recurse on k, n minus 1. Now, to get back the original function, you type this. Let rec choose rec is equal to k comma n goes to choose no rec of choose rec k n. And to print and debug, to see what's going on, you do this. Let rec choose debug 2 is equal to k comma n goes to open curly brace, the print statement from before, then choose no rec, choose debug 2, k, n. Now to truly understand what's going on here, we have to use technique number 3 of writing out the expression, expanding it, and then looking at what happens. Pause the video and try it for both the functions, choose debug and choose debug 2. I really mean that, so please pause the video, write or type out those two functions, and see how they expand for a particular argument, say 2, 3. To help you along, when you see an expression like printf with the string and then 2, 3, semicolon some other stuff, let's call it rest, the way to evaluate it is to write 2, 3 somewhere else in a column, and then continue with the rest expression at the end. Writing a no-rec function isn't so much a replacement for learning the skill of expression evaluation, but more of a shortcut on how to get the information you're after in a way that doesn't mess up your code. Now, you can fix chooseNoRec, and both your chooseRec and chooseDebug functions remain the same, but will work as intended, without you needing to add and delete printfs everywhere. That is, let chooseNoRec equals Recursion, k, n goes to k equals 0 or k equals n, question mark 1, colon, Recursion k minus 1, n minus 1 plus Recursion k n minus 1. Try using everything I have shown you to write a recursive version of direct sum from 1 to n. Like that function, this one should also have the same type, int goes to int. Then try writing a no-rec version of it. If you're feeling up to the challenge, there's an error in our chooseFrom function. It won't terminate on some inputs, which means the expression evaluation won't end, it will keep getting bigger and bigger. Figure out what those inputs are and what you think is a fair answer to return for those cases. Try fixing the function so that it gives this fair answer and terminates for all cases. Justify why you think so using a base case and an inductive step. Is the solution you came up with the simplest and most efficient one? There was a lot to take in this video, so don't worry if you're feeling a little bit lost. Things should become a little clearer in the next video about higher order functions. What we did with no-rec was called untying the recursive knot, and it's a fantastically useful technique, which can apply to different things such as collecting results as well as memoization.